Hi everyone, welcome to Temporal Graph Reading Group for February 13th. Today we are glad to host Katherine from University of Illinois at Urbana-Champaign, who will be um, discussing their recent work called Temporal Graph Neural Tangent Kernel with Graphon-Guarantees at Europe's 2024. And Katherine Tieu is a senior undergrad student at University of Illinois Urbana-Champaign. Her research interests include graph representation learning and trustworthy ML. So I'll pass the mic to you.
Yeah, okay. Thank you, Andy, for your introduction. So I think I'll start sharing my screen.
Yeah, you can test it now.
Okay. Can everyone see my screen?
Yes.
We can see it.
Okay.
Yeah.
Everyone can hear me clearly, right?
Yes, we can.
Yes.
Okay, yeah. Okay, so let's start with the presentation. Yeah, so I'm here today to present our recent work on NeurIPS 2024, which is temporal graph neural tangent kernel with Graphon-Guaranteed. Yeah, so let's start with the motivation. So currently, graph neural network have some limitation, which is complex neural architecture to achieve some powerful expressivity. So for example, in order to capture high order information, such as subgraph or substructure, GNN need to stack multiple layers of message passing, which consists of nonlinear aggregation and self-update modules. And on the other hand, graph kernel have explicit predefined formula, which could be convex, but they have provable theoretical result. And also their specific form is often handcrafted, but may not be powerful enough to support complicated application scenario. So a previous work called graph neural tangent kernel introduced a way to fuse GNN with graph kernel, which could help us enjoy both advantage from GNNs and graph kernel, which are easy training from graph kernel and powerful expressive power from GNN. So overall, graph neural tangent kernel is a family of graph kernel that are corresponding to infinite with GNN that are trained by the gradient descent algorithm. So this kind of graph kernel inherit the advantages from both GNN and graph kernel, which is the expressive power of GNN and the easy training of graph kernel. Also, they also have provable theoretical guarantees from graph kernel. So with those kind of motivation, we would like to extend the kind of graph neural tangent kernel to the temporal setting. So first, I will introduce some preliminaries for temporal graph representation learning. So in a graph that constantly changes with time, we would be interested in first how to obtain the temporal node representation for a node at some time to perform some node level tests. And then after that, we would be also interested in obtaining the temporal graph representation for the whole temporal graph at some time t to also perform some graph level tests, such as graph classification. So first, we start with obtaining temporal node representation. So in this paper, we start with a very simple neighborhood aggregation framework to obtain the temporal node representation, which is for a node at time t, we would aggregate over its temporal neighbors at some time bar t, which is previous, like this kind of temporal neighbor would occur in interaction with v before time t. And for each temporal neighbor, the representation would consist of first the time encoding, which is the time difference encoded in a vector representation. And next, an edge feature, which is the given edge feature of u and v connected at the time before t, and also the node feature of the neighbor. And with the scaling factor over here, we would let this to be the number of temporal neighbor, which turned this into a mean pooling aggregation. But we could also put this at some pooling aggregation by setting C to 1. So yeah, that's how we first obtain the temporal node representation for V at a certain temp. So next, we further process this node temporal representation by introduce some more nonlinear activations. And we decide to process this with additional layers of MLP, which could be represented by this formula. So the subscript L over here would be used for the representation process by L layers of MLP, which could be represented by this formula. And this is just a scaling factor to avoid divergence during the linear transformation. And with that, we could now define the graph level representation. And here we would simply let the graph level representation be the sum pooling over all nodes in the graph. So now, given the graph level representation, how could we devise a similar framework, which is from node level to graph level, using NTK and then kernel regression later on? So what is NTK? So this is the definition of NTK, which is the dot product of the infinite width neural network that process some vector input. And this would be our desired value for the graph kernel, which is the infinite width network that process the graph level representation defined before. And these way are initialized from a normal distribution. So technically, we could not compute this value because there's no way to implement a infinite width network. So we propose a iterative computation process to obtain this value.
Just a quick question. Why do we
Yeah.
want to use an infinite layer network there?
Oh, yeah, because from motivation, using this kind of kernel have some provable guarantees, and we could also match this to the powerful expressive level of GNN without training the neural network. So basically, later on, you can see that we could obtain the prediction just using kernel regression, and we're not training any neural networks here.
Okay, thanks.
Yeah. Yeah, so the high-level idea of obtaining this desired value is that we're first going from the NTK, the corresponding NTK matrix for node level. And then we step by step go through each L layer of MLP and to obtain the final value, which is the summation over the node representation processed by the L layer, the final MLP layer. So yeah, this is the overall framework, which is kind of dynamic programming based. Because first we have a NTK node pairwise matrix for some L layer, and then we want to use this node pairwise matrix to obtain the next node pairwise matrix for the next layer. And we keep doing that until we reach the final layer so that we could obtain the desirable value, which is the neural tension kernel value between two temporal graphs at time t. So first, we need an initialization. So intuitively, the initialization would be the dot product between the node representation. So intuitively, let's say for the very first layer, which is you only have one MLP layer over here. So intuitively, this formula turns into the dot product of nodes representation because you only have one MLP layer over here. So yeah, now you have the initialization, and let's say you already have the previous layer. Let's see how we could obtain the next layer. So this would be the dynamic programming formula, which is the current layer for the node pairwise, which depends on the previous layer for node pairwise, and the pseudo derivative covariant matrix. So first, we identify an intermediate formula, which comprise of the previous layer covariant matrix. And then this is the formula for the pseudo covariant matrix, which could be computed by this formula, which is the closed form of the ReLU activation function. And then similarly, we could also compute the covariant matrix, which is definition, which can be also turned to another closed form of a ReLU function and obtained by this formula. So with the covariant matrix and its pseudo derivative computed, we could plug back to this formula and obtain the next level for the node pairwise matrix neuroattention kernel. So yeah, after we obtain the neuroattention kernel for node pair one matrix at the final layer, we can perform a summation over each node in graph G and each node in another graph G prime to obtain the desirable value for two graphs at MT. So the summation, intuitively the summation node pairwise summation happens is because we're performing the dot product over the sum of node representation in graph G and the sum of node representation in graph G prime. So intuitively, this dot product breaks into the summation of a node pairwise matrix. So yeah, that's how we obtain the desirable value for any two graph at time t. So now we come to the predictions part. So as I said earlier, we would like to use the neuroattention kernel matrix in order to get the predictions without training the neural network by using kernel regression. So this is how we could obtain the prediction using the framework that we just proposed. So let's say our task would be temporal graph classification, which is we would be given n labeled training temporal graphs, and we will be given n labeled training temporal graphs, and we will be interested in obtaining the prediction for any test temporal graph. So first, we construct a graph matrix, n times n graph matrix, in which the ijth entry of this graph matrix is the temp-GNTK value between the graph I and graph J. And then we store everything in this n times n matrix. And then after that, we could use this for kernel regression to obtain the prediction for the test graph as the follow formula, which is first, we construct another matrix, which is 1 times n dimension, consists of the temp GNTK value between the test graph and the n training graphs. And then we obtain the inverse of the graph matrix, and then we multiply this with the label matrix. And this label matrix over here is the label of the n draining temporal graph, which is dimension n times 1. So similarly, we could generalize this to obtain temporal node prediction. So for temporal node prediction, we would have a single temporal graph, and we would be interested in, let's say, a property of a node U at some time t. So again, we could treat this node prior matrix as the gram matrix earlier on this, but on the same graph, because now we only have one graph, and we would be interested in this node property at some time. So we would have a gram matrix over here. And then now the testing time would be treated at the test graph. So we can simply put the value over here and then obtain the kernel regression for the node level predictions.
Just to clarify,
Yeah,
for the middle one, for any test graph, you are doing graph level prediction.
yeah.
You're predicting a binary label or you're doing a regression. So what exactly is the task?
Oh, the test is for the middle one is temporal graph classification.
Okay, so a binary classification.
Yeah, we could do binary class or multiple class, but currently in our experiments, our dataset only support binary classification.
And then for the bottom one, you are predicting what exactly?
Temporal node property. So over here is graph level prediction, and over here will be node level prediction.
Okay, okay.
Yeah,
And here you are working with snapshots or you're working with continuous time?
yeah, we're working with snapshot.
Okay, I see. Okay,
Yeah.
thanks.
Yeah, so with the proposed framework earlier, now we move to the theoretical properties of the Temp-GNTK method. So Temp-GNTK as a kernel itself would satisfy some kernel properties such as symmetric and positive semi-definite, which is proven in these two theorems in a paper. We also found out that the generalization error of our framework is abounded by a data-dependent term, which is presented in this theorem in our paper. And then finally, we found out that our Temp-GNTK value actually converges to the Graphon-NTK value under the setting of growing temporal graph, which is the temporal graph has a growing number of nodes with respect to time. And we start by going to the detail of these theorems. So first, we prove that Temp-GNTK satisfies the kernel property, which is symmetric and positive semi-definite. So symmetric. So yeah, the value for G and G prime equals the value for G prime and G. So that's symmetric. And for a positive semi-definite, we would, let's say we are given n draining temporal graph and any n coefficient, real value coefficient, then we would like to prove this property. And that would be positive semi-definite. And through these two property, we have proven that Temp-GNTK satisfy the kernel property. Next, we would investigate the generalization power of Temp-GNTK. So first, our interest would be this term, which is the generalization error of a graph of any test graph, GT. And this expectation is drawn from a property which is conditioned on its previous snapshot. So basically, this reflects the nature of temporal graph, which is the current snapshot would depends on previous snapshot, which is t depends on previous time before t. So basically this expectation over here is sample over all current snapshot be the empirical term. So this would be the term that we're interested in establishing the upper bound for, and the summation iterate over every snapshot. And here, to keep everything simple, we choose to present with a discrete snapshot. So yeah, we also made some theoretical assumption over here, which is the loss function must be bounded between 0 and 1, and it is Lipschitz continuous. So our theorem state that this generalization error is bounded by a data-dependent term, which is this term, could be obtained by the training data. And this data-dependent term is obtained by the gram matrix that are presented earlier in the obtaining prediction for the graph level task. Next, we investigate the convergence of tangent decay. So under the setting of growing temporal graphs, which is the number of nodes in each temporal snapshot increase with respect to temp, the tangent decay value would converge to an object limit called the Graphon-Guaranteed value with the operator norm. So basically, it could be established in this way. So I will start by explaining the terms in the theorem. So first of all, the Graphon neurotangent kernel, which is acronym is WNTK, is basically NTK, but for growing random graphs. So this theorem states that our tangent TK for two graphs has an object limit, which is the Graphon NTK. So a graphon is could be seen as a random graph generated model, which maps any point sample from the interval, from this interval 0 to 1 to a probability 0 to 1, which is the probability of there's existing an edge between two nodes. So let's say you have an end graph, and then you would divide the 0 to 1 interval into smaller interval, which is represented by these intervals. So basically, let's say you have let's say your graph have n nodes, then the ith node would represent this interval. So when you do sample points, you're basically sampling from these smaller intervals. So in order to construct a graph from the graphon, you randomly sampling from this interval, and then for each sample, you convert the sample number back into the node by seeing which interval this sampling number lies in, and then you determine the edge existence based on the probability. So our theorem states that if two temporal graph converges to graphon when their number of nodes grows, then the neurotangent kernel matrix induced by the temporal graph would also converges to the graphon neurotangent kernel. So yeah. Before we conclude this theoretical property, is there any questions that I need to clarify?
So yes, so I have some limited knowledge about graphons, but basically it assumes this conditional independence, right? So that means that your local connections are not dependent on other parts of the connection that you already built into the graph. Is that correct?
Yeah. You're basically doing some random sample to determine the probability of edge existence.
Right. So I guess
So yeah, Graphon is you can
yeah, sorry, you were saying?
yeah, sorry, go ahead.
Yeah, so my question is, so what happens if you don't have a graphon here? So which part does it break? Which part of the theorem does that break?
Oh, so the Graphon here is used establishing the Graphon neural tangent kernel, which acts as the limit object for our TempGK when the number of nodes grows. So basically, the role of the Graphon here is to be acts as a limit object for our theorem.
Right, right. Yeah, okay.
So
Yeah,
yeah,
yeah, yeah, thanks. So I'm just more thinking about like why would it be specifically chosen as the graphon family rather than a different type of random graph generator model? Um,
I see. So actually, this theorem is extended from a previous work on Graphon neural tangent kernel,
mhm.
which is also cited in our paper. Yeah,
Yeah, okay, thanks.
yeah. Yeah, so next we come to the computational complexity. So in our paper, we also show that our complexity is actually better than some well-known graph kernel method, which is shortest path and random walk. So there's some notation, which is so overall the computational complexity would depend on three factors, which is the number of training graph, the number of vertices in the temporal graph, and the number of edges in the temporal graph. And L over here is the number of MLP layers that are used in our framework. So overall, the bottleneck of our method is uh, the quadratic relationship to the number of vertices. But some well-known graph kernel methods, such as shortest path and random walk, even have more complex computational complexity, which could be you can see that it's bottlenecked by a higher complexity, which is depends on the number of vertices. Like yeah. So finally, we reached the experiments. So over here, I would present some empirical result to showcase how our proposed temp integrate method is operated on reward dataset. So first, we perform the temporal graph classification. So due to the limited dataset of temporal graph classification, we could only perform binary classification over 4 real-world datasets. So we compare against 3 class of model, which is graph kernel, representation learning methods, and temporal graph representation learning. So yeah, overall, we can see that without using neural network training, our method achieves some competitive result over these real-world data due to the limit dataset or experimental setting operated on temporal graph classification is for unchanged label across time, which is we would take into account the whole temporal graph and then predict its label in the final time. So yeah, since the label is unchanged, so we would start by accumulating across timestamp. So so basically what we did in our experiment is that we first divide all the timestamp into 5 sections. This would be, we accumulate the first section timestamp to make the prediction first. and then keep going, accumulate it 2/5 timestamp, 3/5, 4/5, and then accumulate all of them and see how the result varies. And overall, our TemGNTK still outperform other method consistently, no matter at which point we choose to accumulate the graph snapshot. And yes, and as I presented earlier, our framework could also perform temporal node probability prediction. So we choose to evaluate our method on the TGB dataset, which is a very large dataset. So yeah, with our neural network training, we also achieved some competitive result, which is just come behind the best score at that time, which is coming from Daiichi Farmer. So yeah, I think that's all the details for our methods. And if you have any questions, feel free to ask.
Yeah. Yeah, so thanks for the talk and thanks for walking us through the equations and the formulation and everything. So feel free to type any questions you have in the chat, and then so I can ask the question here, or you can unmute yourself to ask the question. Uh, so on my end, I have a quick question on the so on the graph classification side, so what are the tasks on those data sets? Like what is the property you are classifying?
So as I said earlier, the properties is divided into binary class due to limited data set. We
But
didn't find any.
but which kind of property? Like, are you classifying if a graph is infectious, for example, or are you classifying like what exactly is the real world property that's used for classification here?
Yeah, like you said earlier, for example, the infectious network, they would be infectious or not, like over time.
Okay.
Yeah.
And it seems like your method is a very strong one on the graph level, which is very interesting. Um, we also have a like recent work at iClear last year on temporal graph property prediction, but that is not that's also binary classification, but you are predicting the future evolution of the graph instead of you are just taking the entire graph and then you are outputting one binary attribute. So you are so actually making a kind of like a recursive prediction for each week to predict if the number of nodes or edges are growing or shrinking. Um, but yes, in general,
I see.
the
I'm listening.
the graph property is it's a challenging task because of the limitation of data sets as well. Yeah. Okay. So if there's no questions from the audience, we can wrap up the talk here, and and let's thank the author. Thank the presenter again for the great talk today. And we'll see you next week at the reading group. And thanks so
Yeah,
much
thank you,
for
everyone.
presenting. Yeah,
Yeah, thank you for the warm invitation.
yeah, no problem. Thank you. Yeah,
Thank
see you.
you. See you.
Thank
Bye.
you. Thank you.
Bye.
Bye.